In section 6.7, we're going to take a look at another application of definite integral that involves center of mass. So far we've looked at many different applications of definite integral. We've taken a look at area between curves, area under a curve, volume. We've taken a look at arc length, surface area, and work. So today we're going to take a look at a different application of definite integral. Okay, but before we get started, let's talk about mass on a line. So out here what we're trying to do is imagine that you have a plate or something that you want to balance with a finger. Okay, so what we want to do is we want to find the center of mass of that plate, so that way when you put a finger at that point you can balance that plate. Okay, so center of mass acts like as if all the mass of the entire plate is located at a single point. That's what it acts like. Okay, so you're able to balance the plate. So before we can graduate to talking about center of mass of plates, let's first talk about what happens if masses are located on a line and how would you balance those. Okay, so let's pretend that we have something like this. We have a line. You can think of it as a seesaw, and we have a mass over here. This is M2, and we have another mass over here. This is M1. Okay, and there is some point over here, 0, the origin. Okay, and this is where we're going to play the fulcrum, or the pivot. You can think of this as the fulcrum or the pivot. Okay, this distance from 0 is x1, and this distance is at x2 from the origin. Now what's going to happen? Depending upon the masses and how far they are, they're going to cause this seesaw, you can think of it as a seesaw or a line, to rotate. So it might go like this and it might rotate like this. We don't know how it's going to rotate, but depending upon the masses, what size they are and how far they are, it's going to cause the system to rotate. Okay, so the system may or may not be balanced. If it was balanced, it wouldn't rotate. Okay, depending on the size of the masses and their locations and their location. So it may or may not be balanced depending upon the masses and how far they are located from the fulcrum. Okay, so what's going to happen? Each mass exerts a downward force which may turn the system about the origin. Okay, so let me write all of this down. Each mass exerts a downward force which may turn the system or rotate the system about the origin. And the origin is where the fulcrum is located. Okay, so this turning effect is called torque. This turning effect, let me label these things just for notation purpose. Let's call this 1, 2, 3. This turning effect is called torque. Okay, and it is the product of the downward force. It's a product of the downward force and the signed distance of the masses from the origin, of the mass from the origin. So whenever the system rotates, the effect is called torque, and it is the product of the downward force times the signed distance of the mass from the origin. Okay, so the next thing we're going to talk about is system torque. Okay, so the system torque is basically the sum of all torques. I'll call it with a T. Okay, so it is, I'll put it in parentheses here, system torque is sum of all the torques. Okay, so in our case T is going to be, what is the torque of the first mass? It'll be the product of the downwards force, so it'll be force of the first, that the first mass will cause a downwards force, times the distance from the origin. In this case we call that x1. So the downwards force will just be the weight of the mass, weight, and in this case the weight would be what? Mass times gravity, okay, mg. So in this case we'll get, for the first mass we'll get F1, the force, downward force, times the distance, plus the downwards force times the distance for the second mass. So in the first case, remember F, the force, downward force will just be the weight on that end. So in that case the weight is given by m times g. So in this case it will be m1, the mass 1, times g, the gravitational constant, times x1, plus m2 times g times x2. You can pull a g out of the two quantities, so we get m1 x1 plus m2 x2. Okay, now this quantity has a special name. I'm going to denote this quantity by m naught. Okay, and that's called the moment about the origin. So where m naught, which is equal to m1 x1 plus m2 x2, is called the moment about the origin. There's a lot of physics here going on. Okay, so we started talking about torque and now we're talking about moment. Okay, now the next thing we're going to talk about is, remember our goal is to figure out what should be x bar so the system is balanced. Okay, I shouldn't really put the fulcrum here, sorry. Okay, so we want to find out x bar so that the system is balanced. Okay, actually let's just call it the fulcrum for now. So let's take a look at a different example with more masses. Okay, so what we want to do is, in that case the fulcrum was at the origin. Okay, but now let's pretend we don't know where the fulcrum is. Okay, so for the system to be balanced, we want it to be balanced, the system torque should be 0. So for the system to be balanced, the system torque should be 0. So let's take a look at a different example now. So here's my origin. Okay, and I have some masses over here. Out here I have m1, out here we have m3, then we have m2, we have m4, and so on. So we have lots of masses over here. This distance is x4, x2, x1, x3 from the origin. What we want to do now is we want to find out where we should place the fulcrum so the system is balanced. So we want to find out what should this location be here so that the system is balanced. So this is where we want to place the fulcrum so that the system is balanced, or the pivot. Okay, that means it's going to cause no rotation in the system. Okay, so the system torque would be 0. So we want to find this point, x value on the x-axis. Where should that be so that system is balanced? We call this point x bar. Okay, so that's what we'll call, and that's going to be our center of mass. So our goal out here is find x bar, which is a center of mass here for masses located on a line here. Okay, all right, for that to happen, what did we just learn? The system torque has to be 0. So the system torque is equal to 0. Okay, because if the system torque is 0, there's no rotation. Right? So what is our system torque? If you recall, the system torque was the sum of all torques, and each torque is the product of force times sine distance, which is given by this, which we ended up writing it this way. Okay, so let's write all of that down actually. So we get, for the first one, we'll get m1, mass 1 times g. Now that's going to be the sine distance from the fulcrum now, because this is where the fulcrum, in the last example I placed the fulcrum at the origin, now it's placed at somewhere else. So it's a distance from this point to this point for the first one. Okay, so it's going to be x1 minus x bar, plus we get m2 is going to be m2 times g is going to be x2 minus x bar, plus m3 times g x3 minus x bar, plus m4 times g x4 minus x bar is equal to 0. That's my system torque. It is force times the sine distance from the fulcrum. Again, in the previous example, I do want to stress we set the origin. Why did we do that? Because in that case we wanted to place the fulcrum I placed the fulcrum at the origin. Out here it's somewhere else. Alright, so we can clean this up. We can divide everything by g, since there's a g common, so we can divide both sides by g. Alright, and we can also write this in a more compact form. Okay, so I'm going to divide everything by g and write the rest using the summation notation that we did before. So I'm going to go k is equal to 1 to 4, since I have 4 masses. I get m sub k, we get xk minus x bar is equal to 0. So I divided everything by g and wrote the rest that's left using the summation notation. One of the properties of the summation notation is we can distribute. So we get k is equal to 1 to n m sub k x sub k minus summation k is equal to 1 to n m sub k x bar is equal to 0. So we distributed the summation and the m into both of them. Okay, so the next thing we're going to do is we're going to remember our goal is to find x bar where the center where the fulcrum should be placed, or the center of mass. So I want to solve for this guy. So I'm going to move this to the opposite side, the other summation, and then you notice this summation is with respect to k. This has no k in it, so we can pull it outside that summation. And actually, I'm sorry, I'll move this summation to this side, so this negative will become a positive. So we get summation k is equal to 1 to n m sub k x sub k is equal to x bar summation k is equal to 1 to 4. Not, this should not be n, it should be 4, since we have 4 masses. I'm used to writing n's when we did area under the curve. And then we have m sub k. So I moved this second summation to the right hand side. I pulled out a x bar, okay, because it had nothing to do with k, so that's a constant, so we can pull constant out of a summation. And since we want to solve for x bar, I'm going to divide both sides by this, so we get a nice formula for x bar. It is summation k is equal to 1 to 4 m sub k x sub k divided by the summation m sub k is equal to 1 to 4. So that is the formula, but that's only for 4 masses, because I did a very specific formula. So let's in general imagine if we had n masses, what the formula would look like. So if we had n masses, then the center of mass x bar is given by Okay, now remember we are still talking about masses on a line, so we get x bar is given by summation k is equal to 1 to n now, m sub k x sub k divided by summation k is equal to 1 to n m sub k. So here's the formula for center of mass when the masses are located along a line. If you pay attention here, the top of this formula is basically just the system moment. If you recall, moment was given by mass times distance. Do you guys see that? Mass times distance, so that's the system moment. Okay, and this is the system mass, because that's the sum of all the masses of your system. So that is just the system mass. Okay, so let's quickly take a look at an example. So let's say that find the center of mass. I'll abbreviate center of mass as COM. Find the center of mass of weights 5, 10, and 15 pounds located at -1, 2, and -2. Okay. Actually, let's just skip the units so we don't have to worry about them for now. Okay. So we have weights. This could be in kilograms, pounds, and the distances out here could be in meters or it could be in feet, depending upon how the units are given. Okay. So to find the center of mass, what do? We add up all the masses. That'll give us a system mass, and we add up we find the system moment, which is just the sum. We are going to add up the product of mass and distance. Do you guys follow? And that's all it is. Okay, so how do we do this? So the first thing we're going to do is, you can write it as a summation notation, but since we only have 3 masses, we can just expand it and do it. In the bottom, we have sum of all the masses, so it'll be 5 plus 10 plus 15. That'll be the denominator. On the top, we'll have the product of the mass and the sign distance. So it'll be 5 times -1 plus 10 times 2 plus 15 times -2. Remember, it's signed distance. So out here we get, in the denominator we'll get 30, and on the top we'll get -5 plus 20 minus 30. So on the top we'll end up with -15. So we'll get -15 over 30. So my center of mass is located at -1/2. Okay, so that's where it's located. So if you see it, if you want to graphically see it, we have masses located at, so let's say this is the origin. We have 1, 2, -1, -2. So we have masses located at -1 and -2 and at 2. At -1 the mass is 5 pounds, 5 kilograms, whatever units you want. At 2 it is 10, and at -2 it is 15. That's where the masses are. So those are my masses, and at the bottom we have distance. So my center of mass is located at -1/2, so it's located right here. So that is my x bar, and that's where my fulcrum would be to balance these masses. Okay, all right. So that was an example of center of mass along a line. Let's graduate and talk about center of mass in a plane. Okay, so we're going to talk about center. Actually, what did we say before? It was masses on a line. So let's talk about masses in a plane. So we want to find the center of mass if masses are located in a plane. That means in the xy plane. Right now we just did where they were just located on a single line, so in the x-axis. Okay, so we have something like this. We have some coordinate system, y, x, and we have masses that are scattered throughout this plane. So we could have somewhere here, we could have a m1, mass 1. Somewhere here we could have m2, then M3, and so on. They're located everywhere. M4. Okay, this point is given by x1, y1. This is given by x2, y2. This is x3, y3, and this will be x4, y4. What we want to do is find the center of mass of these masses that are scattered in the plane. So the center of mass, just like before, will be some point where you can imagine all the masses are concentrated at. That's what the center of mass means. It's kind of like the balancing point. So in this case, since we are in the coordinate plane, we'll have two values, x bar and y bar. So that'll be the center of mass in this example. So just as before, let's just do the same thing that we did before. Okay, what do we have here? Okay, moment about the x-axis, just like as before. We had moment about the origin. Now we have moment about the x-axis. That'll be the tendency of the masses to rotate about the x-axis. That's what that would be. Okay, so moment about the x-axis would be the tendency of the masses to rotate about the x-axis. Okay, so in this case, it'll be the tendency to rotate this way about the x-axis. So in that case, we want to find our distances would be measured from the x-axis. Before, our distances were measured from the origin. Do you follow? Because we wanted to find the tendency of the masses to rotate about the origin, so we measured everything about the origin. Now we want to measure everything from the x-axis, so we want these distances. Let me use a different color. Do you guys follow? And those vertical distances are called y1, y2, y3, and y4. So in this case, the moment would be, and keep in mind, I've only drawn four masses, but imagine we had n of them. So moment would be given by this. We'll call it m sub x is going to be m1 y1 plus m2 y2 dot 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 plus m3 y3. Remember, moment is mass times the distance from from the axis of rotation, or where it's going to rotate about. Okay, so in our case, it's going to be m sub x times the summation k is equal to 1 to n m sub k y sub k. So that is moment about the x-axis. Similarly, moment about the y-axis will be the tendency of the masses to rotate about the y-axis. Do you guys follow? That'll be the tendency of the masses to rotate about the y-axis. That'll be, so it'll act like it's going to rotate about the y-axis. So we are interested in this distance, how far it is from the y-axis. So we call that distance what? What do we call horizontal distance from the y-axis? We call that x, right? So this distance is x1, this would be x2, and so on. So in that case, the moment is given by m sub y is going to be m1 x1 plus m2 x2 dot 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 plus mn xn. I have no idea why I put 3's here. This should be n, and this should be n. Because we're going to imagine we had n masses, even though I've only drawn 4, but imagine we had n. So the moment in the summation notation can be k is equal to 1 to n m sub k x sub k. So that's a moment about the y-axis. So then we also have the total mass of the system. So the total mass is given by m, which is just the summation k is equal to 1 to n m sub k. That's just the total mass. So the center of mass x bar, y bar is, okay, just like before, what was the formula for center of mass? Well, you took the system moment and divided it by the system mass. But now we have two moments. We have moment about the x-axis and we have moment about the y-axis. To find the x value of the center of mass, please pay attention. It is not m sub x it's tempting because we're finding the x value, so it's tempting to put m sub x, but it's actually m sub y over m, and y bar is m sub x over m. So that is the difference, so please pay attention to those formulas. And the reason for that is because m sub x contains, in this case, where's m sub x? Right there. It contains the y values. Do you follow? So that's why it will give you the y coordinate of the center of mass, and m sub y, if you notice in the formula, contains the x values. So that way it will give you the x coordinate of the center of mass. Okay, so let's quickly take a look at an example. So we want to find the center of mass of weights 2, 4, 6, 8, who do we appreciate, located at -1, 2, 0, 1, 1, 0, and 2, -1. So we have these 4 masses scattered in the plane at these locations. Okay, we want to find the center of mass. Once again, we can use these summation formulas because m sub y is this, m is this, so we divide those two. Or we can, since we only have 4 masses, we can just expand it and do it. So what is x bar? X bar is given by m sub y over m. So it'll be the sum of all the masses. So in this case it will be 2 plus 4 plus 6 plus 8. That's the sum of all the masses. And on the top we have m sub y. M sub y is the mass times the distance from the y-axis, which we always call what? What do we call the x distance? Okay. So in this case we'll get mass 2 is located at -1 x value, 4 is located at 0, 6 is located at 1, and 8 is located at 2. Okay, so that's what we get. If you add them all up, you'll get 20 over 20, which will give you 1. So that's the x coordinate of my center of mass. To find the y coordinate of center of mass, you take m sub x over m. M stays the same, just like before, 2 plus 4 plus 6 plus 8. It's the sum of all the masses. And on the top this time we're going to, since we're finding y, we're going to multiply each weight by its y value. So we get 2 plus 4 times 1 plus 6 times 1 plus 8 times 0. So we get 10 plus 4 is 14 over. 1 second, did I miss a negative here? Oh, this last one is not 0, it's -1 because we have this -1 here. So we get 14 minus 8 would give you, I'm sorry, we have 10, and we have, did I miss a negative also? Let's see. This is 0 for 6, so that's where I went wrong, because for mass 6 it's at 0, 4 is here, 2 is here. Alright, so I'll give us 0 over 20, which is going to give you 0. So the center of mass for this example is x is 1, y is 0. So we've taken a look at 2 examples of center of mass. Okay, the first one is masses scattered on a line. The second one was masses in a plane. And none of these involved calculus. You notice we haven't done any integration yet. Okay, so let's do that next then. So the next we're going to take a look at is center of mass of an uniform lamina. So we're going to specifically talk about uniform lamina. Okay, and I'll explain all of that in a second. So the first thing, before we do this, let's talk about some terminology and assumption. Okay, so the first thing we're going to assume here is that the lamina is uniform. Okay, what does that mean? That means that the density, okay, is the same throughout that lamina. the density is the same throughout the lamina. I should have started with what a lamina is. Let me do that now. Lamina, and I'll come back to that. Lamina is just a thin metal plate. Very, 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 very thin metal plate. Okay, so what does it mean for the density to be the same? That means, imagine I have a plate like this. That means one side is not heavier than the other side. The density is the same throughout that plate. Sometimes you could have laminas made out of different alloys. Okay, so in that case, some parts of the lamina will be heavier than other parts. Do you follow? So that's something we handle in calculus 3 when we talk about functions of more than one variable. But right now we're not going to be able to do that. So we're going to assume that our lamina is uniform. That means it's made up of single material, and it's the density throughout that lamina is exactly the same. Okay, all right, so we have that. So the next assumption we're going to make here is the moment of two non-overlapping regions is the sum of the moments of each region. Okay, remember, moment is basically the tendency of the object of the mass to rotate about a certain axis or the origin. Okay, so if you have two regions that are non-overlapping, then the total moment will be just the sum of their moments. Okay, the next thing we're going to have is, if the lamina is symmetric, then the center of mass is located on the axis of symmetry. And this is extremely important because this will cut down on the amount of work you have to do. Okay, so let me talk about what I mean by that. So for example, let's say my lamina is a circle. Okay, if you think about a circle, so here is my axis of symmetry. What we have on the left, we have on the right, and then we have another axis of symmetry here also. What we have on the left, we have on the right. So my center of mass will be located on the axis of symmetry. In this case, it will be located right there, which would be the center of the circle. If we have a rectangle, okay, you can think about it, isn't this the axis of symmetry isn't that a line axis of symmetry? What we have on the left, we have on the right, but then we also have another axis of symmetry, which is this one. What we have on the top, we have on the bottom, so the center of mass will be located right there. Okay, similarly, let's say that I have a parabola. Okay, and it's chopped off here. So the axis of symmetry over here, you can see, is this guy, right? What we have on the right, we have on the left, but there's no axis of symmetry horizontally because we don't have symmetry horizontally. We only have vertical symmetry here. Okay, so that tells me that my center of mass, at least one coordinate, remember we're talking about center of mass of objects that are two-dimensional, so we'll have 2 points for the center of mass, just like we did over here. We'll have the x and the y value. So in this case, because we have vertical symmetry, okay, whatever we have on the right here, we have on the left. Okay, that means my axis of one value of the center of mass will be located on that green line. Okay, we don't have horizontal symmetry here, but we have vertical symmetry. Okay, I'm sorry, we have horizontal symmetry in the sense like we have what we have on the right, we have on the left horizontally. We don't have vertical symmetry because I can't draw any blue line over here and have something on the top and the bottom be the same. Okay, so that tells me that one value of the center of mass is going to be located on the green line, and that value would be the x value. So we'll say x bar is going to be 0 because that's the origin. Because the x value will be 0, the y bar will change. I don't know what that is. Okay, similarly, let me give you another example. Let's say I have a quarter circle. Okay, so we always look for axis of symmetry. In the last 3 examples, the axis of symmetry were either vertical or horizontal. Okay, but out here, if you notice, the axis of symmetry is this line here, because what we have here is the same as what we have here. Okay, so that is my axis of symmetry, and that's exactly the diagonal line y is equal to x. So my center of mass is going to be located somewhere on that line. Okay, now keep in mind here, this is really cool because we have to find 2 values for center of mass for plates, because you'll have to find the x value and the y. Out here, the x and the y values are the same, so you just have to find the x value. Once we know x, then we know y. Okay, so the center of mass is going to be located on this line, somewhere on this line. So it might be here depending upon how the math works out. So it might be somewhere there. Okay, it's going to be further out. So that's what I mean by axis of symmetry. So whenever you do center of mass, look for that axis of symmetry. If your lamina is symmetric, then you might at least know one value of the axis of symmetry, or you might know something like this where you know both the values are the same. So you just need to concentrate on finding one. In some cases, you might already know one, like this one, x is equal to 0 is the axis of this vertical line, is x is equal to 0. So that's my axis of symmetry. So the x value will be 0. And to find the y value, you'll have to do some work. Okay. The last thing I want to talk about is the density notation. If you recall, density is denoted by delta. We did that in the last section, density of water. And it's defined by, depending upon how we are working, what kind of an object we are working with. Normally, density is given by this. Density, if you're working with a 3-dimensional object, it's given by mass divided by volume. Or if you so this is for 3D. If you're working with a 2D object, it's given by mass divided by area. Okay, this is for a 2-dimensional object, which is what we are going to be working with. So for us, density will be given by that. So for us, density will be mass over area. This would give us a nice formula for mass, which would tell us mass is equal to what? Density times area. So this is something to remember because we're going to use that. Okay, so all the foundation is laid up. Let's go ahead and come up with a formula for the center of mass of a uniform lamina, a 2-dimensional uniform lamina. Okay, all right, so let's take a look at that. So let's pretend for a sake that our lamina is located between 2 curves. So a plate has a shape something like this. So it might be like this. This is y is equal to f of x curve, and my other curve might be like this, y is equal to g of x. Okay, so that is how my lamina is located. So this is my lamina. So it's not a circular lamina, it's not a shape of a parabola, it's not a rectangle, but it's a goofy shape. So I want to find the center of mass of this plate. So I want to find the point on this lamina. If I were to hold a finger, if I were to place a lamina at that, if I were to place my finger at that point, the lamina would be balanced on my finger. Okay, that's what I want to do. All right, so we're going to do the same tricks that we've been working on. This is A, B. What do we do always in the last 5 sections? We take our interval and divide it into subinterval of equal width, and the width is always called what? Delta x. So we start by dividing our interval into n subintervals of equal width, and then we do all the math with that, and then we pretend that we have infinite of those intervals, and that gives us the actual answer. Do you guys recall that? So instead of concentrating on all the subintervals, I'm only going to concentrate on one of them. Okay, so let's just concentrate on this subinterval. So this is going to be my kth subinterval. Whatever I do to this, I'm going to do to every other subinterval. All I have to do is change the number on k. If I take k to be 1, that'll be this subinterval here. If I take k to be 2, that'll be the next one, and so on. Okay. All right, so we're going to work on that one. So this is my lamina. Okay. All right, so how are we going to do this? If you recall the formulas, we kind of already have a foundation for these formulas. We have this and this. So I need to find m sub y, m sub x, and I need to find m, the total mass. So let's start with the total mass first, because that gets used twice. So the first thing we're going to do is find the mass. We're going to find the total mass. So that's what we're going to concentrate first on. So we're going to start by first finding the mass of the kth rectangle. Okay, so let's do that. So let's draw a rectangle here. So I'm going to go up to the curve. Oops, that's a terrible rectangle there. So I'm going to draw two rectangles here, so let's do that. One is to the outer curve. That's this green one. I'm using the right endpoint for my evaluation point, x hat sub k. Do you guys recall that? Okay. So, and the next we are going to use is the blue color for the bottom curve. We don't want the entire rectangle, do we? Of the entire green rectangle, and we don't want the entire blue rectangle. We just want what's in between those two. If I can find the mass of this yellow rectangle, then I'm done, because then I can start adding up the masses of all the other rectangles, correct, next to it. So that's my kth rectangle. So let's first find the mass of the kth rectangle. Is denoted by m sub k, okay, which is given by what? I just gave you the formula for mass. What is mass? Delta times the area. So it's going to be delta times the area of the kth rectangle. Okay, so I should put equal to here. So we get m sub k is equal to delta is a constant, so I can pull it out. Okay, what is a sub k? The area of the kth rectangle. How do I find the area of this rectangle? Well, I would take the green height minus the blue height. That'll give us this. That'll give us the length, and then we multiply by the width. The width is always what? Delta x here. So in this case, it's going to be f of x hat sub k minus g of x hat sub k times delta x. Remember, this is my evaluation point. I erased it, but this is my evaluation point, x hat sub k, the right endpoint we're using always. So you find the height of the function at the right endpoint, the green function, which is my outer one, this one, and then we take the blue function. Then we subtract the blue function from it. That'll give us what's in between. That'll give us the height, the length here, this length here, and we multiply that by the width to get the area of the kth rectangle. Then what do? Then we do what? We have area of m rectangles. I'm going to just skip some steps and kind of fast forward sort of n rectangles, which would be the summation of all of this. And I'm doing this fast because you've seen this pretty much in every section in this chapter. And then we find the actual mass by taking the limit of this. So we get this, and this limit formula is fine, but it's really difficult to use. So we always want to come up with a better way to do this, and the better way to do this was what? We change the limit and the summation to a definite integral wherever we draw rectangles. In this case it will be a to b. Delta is a constant, so I can pull it out. We get f of x hat sub k just becomes x, g of x hat sub k becomes g of x, and delta x becomes dx. So here's the formula for the total mass of that lamina. Okay, so I should really not write total mass, but we should write mass of the lamina. So we found the mass of the lamina. What's the next thing we need? If you recall in these formulas that we first started with, we need to find m sub y, moment about the y-axis, moment about the x-axis. So that's the next thing we need to concentrate on. Okay, so let's go ahead and do that. So let's start with the moment about the y-axis. So let's do 2. Okay, moment about the y-axis. Okay, so that's what we want to concentrate on next. All right, so let's do that. So we're going to again look at just the instead of looking at the entire lamina, that what will be the moment about the y-axis? It will be the tendency of the lamina to rotate about the y-axis, the entire lamina. So we're not going to do the entire lamina. We'll just work on our rectangle. Once we figure out what happens to this one rectangle, we can start adding up all the other moment about all the other rectangles. So we want to figure out what is the moment about the y-axis for just this one rectangle. Okay, so let's do that. So the moment of the kth rectangle about y-axis, which we'll call m sub y sub k, because it's for the kth one, is equal to, how do we calculate moment? It was always given by what? It was always the distance from the axis of rotation times the mass, right? That's what we call the moment, if you recall. It was mass times the distance from the axis of rotation. If it's y-axis, it's rotating about the y-axis. If this is the y-axis, the distance from the y-axis is called x, right? So that's why we had that. So it's a product of that. So in our case, it's going to be m sub k, mass of the kth rectangle, times the distance from the y-axis to the kth rectangle, and that's given by x hat sub k. That's my evaluation distance somewhere. What is mass? Mass is given by rho times a sub k times x hat sub k. Do you guys recall that? We did that a minute ago. Mass was right here, okay, of the kth rectangle. Oops, not rho, sorry. The reason why I put rho is some books use rho for density, but we are using delta. Alright, so we have that. What's the next thing? What is this? We do know a nice formula for that. I just gave you that a minute ago. It was f of x hat sub k minus g of x hat sub k times delta x times x hat sub k. Okay. Then this time I'm going to skip all the other steps. What is the next step we're going to do now? That is just for the kth rectangle. To find the moment of n rectangles, we would take the summation. To find the actual moment, we would take the limit, and then we would change this to integral formula. So I'm going to skip these two steps here now because they're exactly identical, except we're going to use this formula that we came up with. So we get, if I skip those steps, we get m sub y, the moment, the actual moment about the y-axis. It's going to be delta. We get the integral a to b. This becomes f of x minus g of x. This is x hat sub k is just x, and delta x becomes dx. Is that okay? So that is the moment about the y-axis. Similarly, we have moment about the x-axis. Okay. So in this case, what do we get? We do the same thing that we did before. We want to find the moment of the kth rectangle about the x-axis, so the tendency of that kth rectangle to rotate about the x-axis. So we want to find the moment of the kth rectangle about the x-axis. Now we had x hat sub k was our distance horizontally, but how do we don't have y hat sub k. Did we ever use y hat sub k before? So we need to pick one. So what I'm going to do over here is I'm going to say that my y hat sub k is just going to be somewhere the center here. Okay, so that'll be the y value, this will be this y value, so it'll be this height minus this added, take this height plus this height and divide by 2, because it's a midpoint. Do you guys follow? You guys know how to do midpoints, correct? If you want to find, if I give you 2 points, I give you x1 y1 x2 y2, how do I find the midpoint? You add, take y1 plus y2 over 2, and to find the x value we take x1 plus x2 over 2. So I'm just going to use the midpoint there. So let's take a look at that, because I need a y hat sub k. We never use y hat sub k. We have x hat sub k, but we never had to worry about y hat sub k. So we'll call this m sub x sub k is equal to mass. Okay, just like before, it's going to be mass, and instead of this we have y hat sub k. Okay, so how do I find that? Well, that'll just be the average of the top and the bottom values, and the top and the bottom values out here, if you think about it, what is a y value? This is the f of x value, that'll be my y1, and this would be my y2. Do you guys follow? So we would have m is given by delta times a sub k. This would be f of x hat sub k plus g of x hat sub k. I'm taking the top value of the function and the bottom value, adding them up, dividing them by 2 to get that midpoint of which we call y hat sub k. Now we know a. What is a? A is given by f of x hat sub k minus g of x hat sub k. Okay, that was what we called a, times delta x. That's the area, we developed that a minute ago. And then we have f of x hat sub k plus g of x hat sub k divided by 2. This looks familiar. You should see this and this. The 2 I'll pull out, so I'll get delta over 2. If you think about it, isn't this kind of like a minus b and a plus b? Instead of a we have f of x hat sub k, instead of b we have g of x hat sub k. So we can write this as what? A squared minus b squared. So that's what we're going to do. So we get f of x hat sub k squared minus g of x hat sub k squared, and then we have this delta x that's left. Okay, so I multiplied these two things using this and to get that. So that is m sub x sub k for the kth rectangle. Now we do the same thing. We imagine we have n rectangles, and we imagine we have infinite rectangles. So if we go through all of those same steps, we get this formula. Delta over 2 pops out. We get a to b. We get f of x squared minus g of x squared, and delta x becomes dx. So that is the formula. This is the formula for m sub y, and this is the formula for m sub x. Now to find those, hence the center of mass of the lamina is, so let's take a look at it. What is my center of mass? Remember the formulas that we came up with? They were right here that we did. Oops, right there. X is m moment about the y-axis over m. So we get x bar is m sub y over m, and y bar is m sub x over m. So this is where the integral comes in. What is m sub x? M sub x is right here, this formula. I'm not writing that whole formula down again. And then m sub y is what? M sub y is right here to find x bar. Okay, so these are the two formulas that we're going to use, where m sub y, m sub x, and m are given above. I just derived them for you. So let's do some examples. Okay, so let's start with the simple one. So let's say we want to find the center of mass. Okay, keep in mind, actually let me go ahead and give you those formulas to show you something interesting that happens. So let's actually do that. So what is x bar? If you think about x bar, it's m sub y. What was m sub y? If you recall, it is right here, this guy. What is outside here? Delta. And what are we going to divide m sub y by? M. So what is m? M is right here. It also has a delta. So we can cancel those delta, so the density doesn't even come into play here. So x bar is just going to end up being the integral a to b. Okay, you're going to have x times f of x minus g of x dx divided by the mass. The mass is given by a to b. We have f of x minus g of x dx. If you notice the deltas that were in the front, they cancel from the top and the bottom. Similarly, the same thing happens for this one, except there's a half in the front still, a to b. We have f of x squared minus g of x squared dx for the top, and on the bottom it's the same mass, so we get f of x minus g of x dx. So that is the actual formulas. So I did write them down eventually, but remember the deltas in the front cancel, so we really don't need to worry about the density at all. You can just completely ignore it. Is that okay? All right. So let's take a look at how to find the center of mass for a parabola. So let's do that. So let's say that find the center of mass of a lamina bounded by the curves y is equal to x squared and y is equal to 4. Anytime you do a center of mass problem, please make sure that you are taking you're checking to see if there's any symmetry. Okay, so please make sure you guys do that. Okay, so I'm already running over time, but I'm going to finish this up. Again, remember, I've always told you, you don't always have to watch the videos all in one sitting. You can split them up. So here's my parabola, y is equal to x squared. Here's my line, y is equal to 4. Do you see symmetry? We clearly see symmetry here, correct? So we can say by symmetry, we know one value of the center of mass, which is what? What do we know? That the x value of the center of mass will be on this line, because isn't this the line of symmetry? That line is what? X is equal to 0. So the x value of the center of mass is going to be 0, because that is my axis of symmetry, which is the x is equal to 0, so x bar will be there. All I need to do is find the y value. That means I'm looking for this value, so I need to find these two integrals up here, this one and this one. So let's start with the mass first. So m is the integral. So I need limits of integration here. So if you look at this, if you solve these equations simultaneously, if you replace this y with 4, you'll get what? 4 is equal to x squared. So we get x squared, x is equal to what? Plus or minus 2. So this point over here is negative 2, positive 2, and this point over here is 2. So we're going to integrate from negative 2, to 2. Or we can go from 0 to 2 and multiply it by 2 and use symmetry. So that's what I'm going to do. I'm going to go 2, 0 to 2. You can go from negative 2 to 2 also. You take the top curve. F of x is always the top curve. So in this case, it's 4. Okay, minus the bottom curve, which is x squared dx. Okay, this is a simple term by term integral. I have it done, so I'll give you the answer. You get 10.67. But you can easily integrate this. You get 4x minus x cubed over 3. Plug in the upper limit and the lower limit, and you'll get that. So that is the mass of that lamina. Now we need to find m sub x. Remember, this is called m sub x. Okay, so what is m sub x? So let's write that formula down. And we get, so that is the mass. I'll underline it. We're not going to box it because we need to find m sub x first. So m sub x is 1/2 the integral a to b. We have f of x squared minus g of x squared dx. That's what m sub x is. So we get 1/2. Again, we can use symmetry, so we'll multiply this by 2. Instead of going from 0 to negative 2 to 2, we'll go from 0 to 2. f of x, which is always the outer curve, which in our case is 4 squared. G of x is what? X squared squared dx. Once you do set up the mass integral, this will always be f, this will always be g. So you know them, so you don't have to do any more work. 2's will cancel. Once again, you can integrate this. This will become a 16. This will become an x to the 4. You can do term by term. So just again, for the sake of time, this is going to give us 25.6. That's m sub x. So what is y then? So I'll underline that too. Y is going to be, y bar, sorry, it's going to be m sub x over m. Okay, so in our case, it's going to be 25.6 over 10.67, which is going to give us 2.4. So my center of mass is going to be x is 0. Remember, from symmetry we knew x bar was 0 and y bar is 2.4. So if you go back to that picture and look at it, so this is 4 if you recall, because that's the line y is equal to 4. This will be 2. So 2.4 would be somewhere here. So my center of mass is located here, which makes sense. It'll be more towards the bigger side. Okay, this side is a lot bigger here than this. Okay, all right. Let's take a look at one more example. Okay. So let's say I want to find the center of mass. Find the center of mass of a quarter circle of radius, let's do 2. Okay, so let's draw the picture. So we have a circle like this. This is 2, this is 2. We're only looking at the quarter circle here. Okay, this equation of a circle is what normally for the entire circle? It's what? X squared plus y squared is equal to r squared, where r is the radius. In this case it's 2, so it'll be 4. And if you solve for y, we get y is equal to plus or minus the square root of 4 minus x squared. You move the x squared over there and then take square roots on both sides. Since we are above the x-axis, out here the y value is always what? Positive, so we can ignore the negative radical. We'll just take a look at this one. So this is the equation of this curve here. Okay, all right, now that we know that, how do I find the center of mass? Anytime they ask you to find the center of mass, the first thing you ask is there any symmetry here? Can I draw a line such that the region is symmetric? If you notice, if I were to draw a line here, this is the axis of symmetry, and this line is what really? This line is y is equal to x. So what does that tell us? If I can find either the y value of the center of mass or the x value of the center of mass, they're both going to be the same. I don't have to find the other one. So my center of mass is going to be living on this line somewhere. So let's find it and see where it is. So to find the center of mass, I need to find the mass first, and the mass is given by the integral a to b f of x minus g of x dx. Now let's take a look at it. F of x is your outer curve, and where are we going to integrate from? From 0 to 2. Okay, the curve goes from 0 to 2 here. F of x is the outer curve, so this is my outer curve, which is given by this. So we have square root of 4 minus x squared minus the inner curve. The inner curve would be this bottom one, which is what? Y is equal to 0. Isn't that the bottom curve? So we have 0 dx. So we end up with this integral. Sadly, in calculus 1, we have no way to integrate this. Even though it's a composite function, if you try to substitute for the inside, you won't be able to eliminate all the x's. But you recognize that this integral is really the integral for what? Area of a quarter circle. Isn't that the integral of that? Isn't that what we have here, quarter circle? Okay, because this mass, really, if you remember, go back before, mass was what? Delta, density times area, but the density canceled out. Do you guys remember that? So we didn't have to worry about density. So this mass is just the area. So this is the area of a quarter circle. So from geometry, even though I cannot integrate this in Calc 1, I do know from geometry how to calculate area like we did in section 5.4. So in 5.4 you did that. So if you go back and look at it, where you were just given a region and you wanted to find the area, so the area is going to be, it's a quarter circle, so we're going to take 1/4 times the area of a circle, which is pi r squared. R is 2, so we get 2 squared, so these will cancel. So my mass is the same as my area, which in this case is just pi. Okay. The next thing I want to do is I want to find m sub x. Okay. And why am I choosing to do that? The reason for that is because if you look at m sub x has a square in it, and that'll come useful because of this radical. So when you square that radical, the square root will disappear, and that'll help us integrate it much easily. So I always like to underline things that I've already found. So let's do m sub x. M sub x is 1/2 the integral a to b f of x squared minus g of x squared dx. Okay, f of x and g of x are the same as what you started with up here with the mass. This would be f of x, this would be g of x. So you don't have to reinvent the wheel. The limits of integration are also going to be the same. Once you do one integral, everything else is going to be the same. The only thing is the integral formula might change a little bit. So in this case, f of x is going to be square root of 4 minus x squared squared. G of x is just 0 squared dx. So you can see why I use this one. You can, the square and the radical will vanish. So we'll just end up with this 0 to 2, 4 minus x squared dx. This is a simple term by term problem. And if you integrate this, you'll end up with 8/3. Okay. So what is my y value for the center of mass? Is given by m sub x over m. That's how we define that. So in this case, it's going to be 8/3 over pi. So it's going to be 8 over 3 pi. Okay. And what did we know from symmetry? From symmetry, we know that x bar and y bar are the same. So the center of mass for this is going to be 8 over 3 pi and 8 over 3 pi. Okay. So that's what the center of mass is going to be. And if you wanted to, we can quickly take a look at it to see what it is exactly. So you take 8 divided by 3 pi. So we get 0.88 roughly. So if you go back out here, this is 2, this is 1, 0.88 would be here. So if you go up to this line, this is where your center of mass is for this lamina. Okay. All right. I'll do one example which is not on the axis of symmetry. So let's take a look at that. So at least you get to see something different. Okay. So let's say that I have the lamina, find the center of mass of a lamina bounded by the curves y is equal to x minus 1 and y is equal to 1 minus x squared. Okay, so let's take a look at that. Let's graph both of them. This is an upside down parabola. So it looks something like this. This is 1, this is 1, this is minus 1. So that's the first one. The second one is just a line. The x-intercept is 1 and the y-intercept is minus 1. So it's right here. This is negative 1. So it goes like this. Okay. So that's what that lamina looks like. So this is what that lamina. And you can see there's no axis of symmetry, or is there one? So what do you think? Is there an axis of symmetry for this? Okay. So because this region on the left is not the same as this region on the right, so we can't use x is equal to 0 there because this goes further down. So keep that in mind. So there's no axis of symmetry here. Okay, so I need to find all my masses, all the things to do this problem. So let's quickly set this one up, and this will be our last problem. We get m. The mass is given by this integral a to b f of x minus g of x dx. So where should we go from? So we need these points of intersection. Do you guys follow? This one we do know it's 1, but we need the other one. So we set these two curves equal. So we get 1 minus x squared is equal to x minus 1. So you can rearrange this. Okay, so what do we end up with? I'll move everything to the right side. So we get x squared plus x minus 2 is 0. So we get x plus 2 times x minus 1 is 0. So we get x is equal to 1 and negative 2. So at this point, I haven't drawn these pictures accurately, but this point here is going to be negative 2, x is negative 2 and something, and this is 1 and something. Is that okay? So we want to integrate from negative 2 to 1. The outer curve will always be the top curve. The top curve is the parabola, which is this guy. 1 minus x squared minus the inner curve. The inner curve is this line, the one below, which is x minus 1. Make sure you guys put parentheses because there's a negative in the front, dx. You distribute the negative and do everything term by term, and I'm not going to waste time doing that, but I will just give you the answers. If you did that, you'll end up with 9/2. So that is the mass. You just have to distribute the negative and integrate term by term. So we found one thing. Again, underline it, what you find. We're not going to box it because that's not our answer. M sub. The next thing we're going to do is find m sub x. What is m sub x? We had that handy dandy formula for that. It was 1/2 times the integral a to b f of x squared minus g of x squared dx. Once you set up one integral, everything is going to be the same. So we get 1 negative 2 to 1. And then this is f of x, this is g of x. So you just square them. You take f of x squared minus g of x squared dx. Now this integral will take a little bit to do. It's not difficult. You'll have to expand this. You get 1 minus 2x squared plus x to the 4th minus, you get x squared minus 2x plus 1. You distribute the negative, collect the terms, and then you end up doing it term by term. So if you do that, you get negative 27 over 10. So that is m sub x. Okay, next we want to find m sub y. Now this is something we haven't done yet, so let's do that. The formula for m sub y was this: a to b x f of x minus g of x dx. That was a formula we came up with for m sub y. Again, the limits are always the same. In this case, it's negative 2 to 1. We have x. F of x was 1 minus x squared. Again, please make sure you guys use parentheses because of the negative signs. Dx. You distribute the negative, collect the terms, and then multiply everything by x, and then do term by term. So if you did that, you would end up with negative 9/4. So that's m sub y. And we're not done because none of these are answers. So x bar is going to be m sub y over m. So in this case, it's going to be negative 9/4 over m. M was 9/2. So we end up with what? Negative 1/2. The 9s will cancel and the 4 and the 2 will cancel. We get that. And y bar is going to be m sub x over m. M is 9/2 and y was negative 27 over 10. So we'll get 5 and 3, so we get negative 3/5. Okay, so that's what you should end up with for that, which is negative 0.6. So my center of mass, my final answer, is going to be negative 1/2 and negative 3/5. Okay. Alright, so that's how we find the center of mass of a lamina. There's one more topic that's left, which is basically the theorem of Pappus. I think I'm going to skip it this semester. So if you have homework problems that deal with theorem of Pappus, you can skip that part, okay? So to do everything else in that section that's assigned to you, but you can skip theorem of Pappus.